Okay, when you look at chapter 4, all right, first you have to look at what is thermal equilibrium, definition of thermal equilibrium, and then you must understand ideas of how to look at thermal equilibrium idea. Then the object that increase the temperature of the object is in context shows a higher specific heat capacity. You must know that also. Okay, first definition as usual, thermal equilibrium. Two objects in thermal contact, heat energy flows from a high temperature to a low temperature and they reach the same temperature. Things to look at it again is like this. You know the formula that Q is equal to mc theta. So any objects that have a smaller specific heat capacity, they shows a higher increase in temperature, right? Excuse me. Object with a lower specific heat capacity shows a higher increase of temperature or higher changes. Shows a faster heat loss to the surrounding or heat gain, higher increase in temperature. What are the factors that affect the rate of increase in temperature? So as you know, Q equals to mc theta. So theta should be equals to Q over mc. So the factors that influence the changes of temperature should be the mass of the object. Number one, mass of the object. Number two, specific heat capacity of the object. And quantity of energy given. What is the quantity of energy given? So these are the main factors that will influence the changes of temperature in an object. So object undergoes changes in temperature based on the mass of the object. A smaller mass of object and a bigger mass of object, if they are exposed to the same amount of heat energy, the smaller mass shows a higher increase, right? Then specific heat capacity, as you learned just now, the smaller the specific heat capacity, the higher the increase or changes in temperature. All right. So we are looking at quantity of heat energy. Two objects, same mass, same materials, everything same. If they are exposed to heat energy, an object with a higher exposure of heat energy shows a higher increase in temperature. Okay. So you must know that. Okay, next, see here. This is a very common question. Okay, state how a liquid glass thermometer can be used to measure the body temperature of a sick person. Explain heat transfer that takes place at each stage of measurement. So always remember, when you have a thermometer, the heat energy from the body or externally from the thermometer flows to the liquid of mercury in the bulb. So the heat energy from outside flow inside. So the liquid of mercury absorb the heat energy and the liquid of mercury will expand. When the net heat flow between them is zero, when the net heat flow between the external body temperature and the heat and the mercury inside the thermometer is zero, expansion will stop. The liquid mercury in the thermometer and the body has reached the same temperature, right? So we realize the thermometer is able to measure the body temperature. So again, if you look at it here, so we have a thermometer where a thermometer will have its bulb. Right? And inside there, liquid mercury will be there. Right? Liquid mercury will be inside here. Right? This liquid mercury will show expansion. So as the heat energy flows through the liquid mercury, it will show expansion. It will start to expand. The liquid mercury will expand until it shows the net heat flow is zero. When the net heat flow between the liquid inside here and the external temperature is equal, so they have reached the same temperature. The liquid will stop expansion. The liquid stop the expansion. This is how we measure the body temperature. We are able to measure the body temperature. This is how we are able to measure the body temperature. Okay. Any question, anyone? Boleh? So, first idea, yes.
How to count the, the thermometer, they got what fixed point thingy one? They want count the length, all those one. How to count that one?
Okay, can. Wait, okay. This one done. So we understand how we can use a thermometer to measure body temperature. So application of, Mr. Chu, I'll come back to that in a while. Application of thermal equilibrium. So as I said earlier, object with lower specific heat capacity is a good conductor of heat. All right, they show higher changes in temperature. Object with a bigger specific heat capacity is a bad conductor of heat. They show a smaller changes in temperature. Okay. Beside this pressure cooker, you also must know about this baking oven. Because baking oven questions, they can include the idea of heat, the idea of electricity, the idea of pressure, everything they can include. Idea of pressure, heat, and also electricity. So when you have a baking oven, try to understand, there will be a filament of heating filament in a baking oven with the property of heating element such as coiled, longer length, thinner wire, and also higher resistance, higher resistivity. As the heat is generated inside the baking oven, the whole oven which is closed now will experience a high increase in temperature inside the baking oven. So the whole heat inside the baking oven is able to cook or bake whatever we are baking. All right. This is the whole idea of a baking oven. So baking oven shows that the volume is fixed. Baking oven shows the volume is fixed. Even pressure cooker volume is fixed. Increase in the temperature of the air inside baking oven will push the air particles to move to expand, but volume is fixed. So they will experience a high increase in temperature, a high increase in pressure inside the baking oven. All right. Okay. Next is what I did. Sorry. Next is the properties of the liquid. Okay, wait. Do I have that question? Wait, Mr. Chu. I check. Do I have that question? No. I don't have that question. Okay, let's Mr. Chu. I think you were asking about this. Okay, let me explain. Okay, this is a non-calibrated thermometer. Non-calibrated thermometer. All right. The reading was 0 cm when it is at a lower fixed point. Lower fixed point is 0 degrees Celsius. Lower fixed point is the freezing point of ice. And then when the same non-calibrated thermometer is placed in boiling water, upper fixed point, we realize this reading is exactly 24 centimeter. Now, at one point, we place this thermometer, all right, inside a heated water. Inside a heated water, we realize that it started to show length of mercury, all right. Length of mercury started to show equal to, let's say, here, length of mercury expanded up to 22 centimeter. So what should be the temperature? Mr. Chu, are you asking questions like this?
Yes.
Okay, so what we have here is that, see again, so we have a system where, All right. Initially, the temperature was 0 degrees Celsius when the length of the mercury also 0 cm. Now, when the temperature is 100 degrees Celsius, the length of the mercury is 24 cm. Okay, 24 cm. So what happened here is that when the length of the mercury that expand now reaches 22 cm, 22 cm, what should be the temperature? In each soalan there. So the thermometer that we are using is a non-calibrated thermometer. So what we do here, see here, okay, we take 24 centimeter length of expansion of the mercury is equal to 100 degrees Celsius, all right, changes in temperature. So every 1 centimeter changes in temperature or expansion of mercury, every 1 centimeter expansion of mercury is equivalent to 100 over 24, 100 over 24, okay? So what happened here is that now the expansion is 22 cm. So the temperature recorded should be 100 over 24 times 22. What we get, Mr. Chu?
$91.67.
Yep, 91.67 degrees Celsius. Okay, done. Another example I give Mr. Chu. See here. Let's say this is the thermometer. Okay, and it is a non-calibrated thermometer. Okay, this is the 0 cm. Okay, and this is the 4 centimeter length. All right. When we place the thermometer in ice cubes, all right, or lower fixed point, we realize that the temperature is 0 degrees Celsius, so the length of mercury expanded is 4 cm. Now the same non-calibrated thermometer we placed in upper fixed point boiling water. Upper fixed point boiling water. All right, we realize now the length of the mercury inside here is a perfect 29 centimeter. 9 centimeter. So if I take this non-calibrated thermometer and I put in a liquid which is having a temperature of 80 degrees Celsius, all right, what should be the length of expansion of the mercury? What should be the length of expansion of the mercury? Can you all calculate for me, please?
Twenty cm.
20 cm. Yep, 20 cm. So the whole idea here, it shows that the length of expansion, was 25 cm, all right? length of expansion was 25 cm for a changes of 100 degrees Celsius. So for every 1 degree Celsius changes in temperature, length of expansion must be 25 over 100. So now when the temperature shows 80 degrees Celsius, all right, then it should be 20 cm length of expansion, all right? But what is the answer here? If I put here X, so what is the answer here? The answer must be 24 cm. Why 24 cm? Because you have to plus back the 4. 4 plus the, because the expansion here from 0 to here was 20 cm. 20 cm is here. So the total length here will be 24 cm. Okay, done with this question. Mr. Chu, you get it?
Yeah.
Okay, done. Okay, property of a certain liquid that we normally don't see properly. What is a volatile liquid? They will have a very low boiling point and they can easily evaporate at room temperature. Heat required by liquid during evaporization is absorbed from surroundings. So if they are vaporizing, they are actually taking the heat from the surrounding, all right? Which results in cooling. That's why when we sweat, we feel cool, all right? Called cooling by evaporation. Evaporation occurs when faster moving molecules near the surface escape out of the liquid, right? The average speed and average kinetic energy of the molecules left decreases due to fall in the temperature. Okay, please go through this. Okay, next, which we learned earlier, uses of specific heat capacity. See here, application of specific capacity. So substance that having a small specific heat capacity, see carefully. Any substance that has a smaller specific capacity can be quickly heated up, can experience a big change in temperature even though only a little heat is supplied. They are mainly used as cooking instruments, frying pans, pots, kettles, and can be heated up quickly. Substances having large specific capacity undergo small heat change while heat is released or absorbed. They are normally heat storing instruments. They also can be insulators, water, one of it, and also cooling agents. All right. We have a few calculations here. Okay, let's try all these calculations. All of you try. Muller. So if you look at here for number one, the answer was 6.4 times 10 to the power 5 joules. It's just a direct formula of ml. Number two, there are two stages here. First is the ml. The ice is melting. The second point is the temperature is increasing, mc theta. So you have mass of the ice times the latent heat of fusion, and then mc theta law. Okay, next. So this is the answer for number two. Number three, this is a 4 stages system. First, the ice cube shows increase in temperature from -15 to 0. Then at 0, the ice cube is melting. Then after all the ice cube melted from 0 degrees Celsius, it's now in the form of water increased to 100 degrees Celsius. Then finally at 100 degrees Celsius water, all the water are boiling, becoming steam. So mc theta plus ml plus mc theta plus ml. So you get the whole thing lah. That's the answer, 1685750 joules. Okay, and then number 4, this is actually volume against temperature. So it should be V1 over T1 equals to V2 over T2. So you get the whole idea, okay? Initial volume 20, initial temperature 37. So 37 you must change to Kelvin because this is actually in Kelvin. The volume is in meter cube, right? But the temperature must be changed to Kelvin, all right? What is the name of this law?
Charles law.
Charles law. All right, thank you. So now the final volume found to be 23.226 meter cube. But the question one, what is the increase in the volume? They want to know what is the increase in the volume. So the increase in the volume will be 3.226 meter cube. All right. Okay, next. Okay, next. Done with this one. Okay, we're going to explain car radiator system. Okay, as you all know, every car system will have a cooling liquid system. The cooling liquid system shows that, okay, the coolant liquid will move around the engine, then go to its pump system, and then come back. That's why you'll be surprised to see why car engine got water pump. They use the term water pump at the back of the engine on. So the coolant liquid goes back and they flow back to the engine and come back as a hot liquid, right? Okay, hot liquid, and they move back. So the whole radiator system will have, okay, this system. So the coolant. So we are going to look at mechanism of car radiator system. Okay. So first of all, heat energy from the car's engine will be absorbed by the water flowing to the hot engine part. It's called a coolant system. There's a special piping around the engine, right? And the coolant or the water becomes hot. Then it will be sucked by the radiator fan, which will cool down the whole water system. And the water that has been cooled down will flow back to the engine, to the hot portion of the car, and this process repeats. So it's a cycle. The liquid goes to the engine, the liquid becomes hot, then flows to the radiator, the heat is released to the surrounding, it becomes cold, goes back to the engine, and the whole process it's repeated, right? So water is one of the best, but of course it's a cooler liquid with a mixture of chemicals that we're using. Okay, you just did this question recently. Characteristics of hydraulic liquid used in car radiators. Yes, Mr. Yi Cheng, one of the characteristics is actually it should have a high boiling point. Okay, first is high boiling point. Next should be what? Let's have an interactive class now. Okay, one is high boiling point. Next.
High specific heat capacity.
High specific heat capacity. Lagi.
Chemically inert.
Chemically inert. Lagi. Anything else? So the hydraulic liquid used in the car radiator, the chemical must be chemically inert so that it will not form any chemical reaction with the transfer tube system, prevent leakage. It must have a very high boiling point, therefore it can withstand the high temperature in the flow system. It will not vaporize easily. Okay. Very high specific heat capacity. It is able to absorb or transfer high quantity of heat energy. Able to absorb or transfer high amount of heat energy. Next. Look at this basic question. These are the repeated questions most of the time. What is meant by heat? What is meant by temperature? Heat is a form of energy and we measure by using joules. Temperature is the degree of hotness of an object and we measure by using Kelvin. Temperature must use Kelvin. Okay, then describe the working principle of a thermometer. Just now earlier we explained already. There will be a contact. The bulb of the thermometer will be contact with the body. Wherever you put it, the heat energy from the body flows to the liquid mercury through the glass bulb. The liquid mercury absorbs the heat energy. So this is called thermal contact, right? The liquid mercury will expand. Expansion stops when the net heat flow is zero. The liquid mercury and the body will have the same temperature. We are able to measure the body temperature. Okay, so done. Thermoequilibrium. How thermometer can measure human body temperature? Same lah, principle of expansion of volume of a liquid with respect to temperature. So all this done, the heat from the patient's body will transfer to the thermometer, then the thermal equilibrium is attained. Temperature of the thermometer and the patient is the same. The thermometer will show the temperature of the patient's body. Okay, done this part. Now look at another question pula. All right. A resistance thermometer has a resistance of 70.5 ohms at ice limit. Ice limit is 0 degrees Celsius and 141 ohms at the steam limit. Steam limit is 100 degrees Celsius. When this thermometer is inserted into a liquid Y, the resistance becomes 120 ohms. What should be the temperature of the liquid? Okay, let's solve this. So I'm solving number 12. So non-calibrated system like just now. So when the resistance was 70.5 ohms, it was at ice limit 0 degrees Celsius. When it's a steam limit, which should be 100 degrees Celsius, the resistance shows 141 ohms. And now it is in a liquid called liquid Y with a resistance of 120 ohms. What should be the temperature? So what we're going to do, we're going to take 141 minus 70.5. We get 70.5. So we know now that 70.5 ohms, from 141 to 70.5, guys, it's 70.5 ohms. So 70.5 ohms are equal to 100 degree Celsius in changes of temperature. So now we're going to measure expansion or changes from 70.5 to 120. So 120 minus 70.5, we end up getting 49.5. So we know every 1 ohm resistance is equivalent to 100 degrees Celsius. Divide by 70.5. Now we know the expansion, the changes in resistance is by 49.5 ohms, which should be equal to 100 divided by 70.5 times 49.5. What are we getting, guys?
$70.22. Sorry, 21.
Yep. We're getting 70.21 degrees Celsius. So that is the temperature, 70.21 degrees Celsius. All right. Okay. That's for question 12. We are solving question 12. Now let's try question 13. Question 13. Huh? Okay, all done. Huh? Anyone got any question here?
No.
Okay, number 13. Thank you. The air pressure in a container at 42 degrees Celsius is 2.4 times 10 to the power 5. The volume is, the container is heated until the temperature 52. What's the final pressure? So now we're looking at pressure and temperature. So now we're solving number 13. Pressure and temperature. So initial pressure was 2.4 times 10 to the power 5 Newton per meter square. Initial temperature was 42. But as we know, must change to Kelvin. This is pressure law. Final pressure, we do not know. We know that the final temperature is 52. We change this also to Kelvin. So what should be the final pressure? Anyone?
2.48 times 10 to the power of 5.
Can you repeat it again?
2.48 times 10 to the power of 5.
Pascal or Newton per meter square. So this is pressure law. All right. So pressure law, Charles' law, must change the temperature to Kelvin. Okay, anyone got problem with this usage of this formula?
No, not at all.
Okay, very good. Okay, talking about chapter 4 again. All right, based on your final past year questions, let's go through again chapter 4. Chapter 4. Gas law came out in section A in 2018, right? 2019, section A of, I'm talking about paper 2 only now. Paper 2, section A memang ada soalan lah. Okay, 2019, section A. B and C langsung tak ada soalan. Okay. So, if I look at it here, based on the past year question, all right, 2017, question 9, section B. And then 2018, question 11, section C, right? So, nothing much. You can see. But if you ask me, I'll tell you this chapter is easy to prepare also. You just go through all the gas laws properly. Make sure you know all the gas laws properly. Make sure you know how to calculate. Get ready with the experiments to determine these gas laws also. Okay, experiments. All right, gas laws like Selangor, I think so, came out with the pressure gas law and also all these like volume and temperature. Okay, all this you all have to prepare. Okay, that's for paper 3 idea. For paper 2, my concern is normally more on paper 2. Paper 2, I feel like you should look at, right, on all the specific heat capacity, how to determine specific heat capacity, or how to determine specific latent heat of fusion or specific latent heat of vaporization. All this should be a good part that you must go through properly. Okay, all right. Okay,